Hello, class. Okay, so we're about to start the second section of the class, which consists of 3 chapters. And this section consists of electricity, basically. Alright, so electricity is something that has been known for quite a long time. Like even kind of ancient times, they noticed that if you rub things together, sometimes you can exert forces. For example, like materials that were common back at the time, like fur. I have a table here, I'll explain what this is later. But say you have like fur and glass. And say you have a glass rod and you rub it with fur, you can exert forces on things with that glass rod. These are very small forces. Now it turns out, I'm going to go back, this is a little out of order, but in the entire universe, as far as we know to this time, there are only 4 fundamental forces. So fundamental forces, we have gravity, the electromagnetic force. So this is, finish this. So yeah, in this section we're talking about electricity. Next section we're going to talk about magnetism. And we have since learned that these two are actually different aspects of the same force. So it's called the electromagnetic force. And then there are 2 nuclear forces, which are just called the weak nuclear, or sometimes just the weak force, and the strong nuclear force. Now, this is it. As far as we know, these are the only forces that govern our universe. Or I should say 4 fundamental forces. And really in this class, we only talk about gravity and the electromagnetic force. The nuclear forces, just as an example of a nuclear force, if you look at the nucleus of an atom, it's filled with protons. So you've got all these protons in here. And these are all charged particles that are exerting repulsive forces on each other. And so it turns out these forces are very strong. And so that would, of course, what's holding the nucleus together? And it's a strong force. There's another force called the weak nuclear force that's involved in some types of radioactive decay. But that's it for the forces that govern the universe. Now, you might hear, like, what about tension or something? Like in mechanics, say we have a box or just some mass that's suspended by a string. So we say there's tension in the string. Well, yeah, tension is a real force, but it's not fundamental. What this actually is electromagnetic in nature. Most forces are electromagnetic in nature. So I want to talk about, like, these are the 4 fundamental forces. And gravity is an extremely obvious force. We're constantly aware of it. We can always feel its effects. Magnetism or electromagnetism, not quite so obvious. However, what's interesting is this electromagnetic force is extremely strong. We're going to see an example of just how strong the electromagnetic force is. But it's much harder to notice. And we're also going to learn very soon why it's harder to notice. And then these nuclear forces, they pretty much have no effects unless you look on an atomic level. So, yeah, the electromagnetic force, I mentioned this, if you just take a glass rod and rub it with fur, you can exert forces, but they're extremely small. Like you could pick up a really tiny particle, like maybe a piece of styrofoam, which is very light. So you might think gravity is a much stronger force, but that's actually not the case. So it's kind of interesting that electric forces are much stronger than gravitational forces. Just not nearly as noticeable. So anyways, this was noticed in ancient times and kind of like a curiosity. Probably didn't seem all that important because again, the forces are not very significant. But some really important work was done in the 1700s by a guy named Charles Dufay. I'm sure if I'm getting this name right, if that's supposed to be capitalized or not. But anyways, in the early 1700s, Charles Dufay did some experiments, and he noticed some important things about electricity. So, just to go over a couple of the experiments that he did. Let's say we have a glass rod. And say we have a metal object. So this is metal. Okay, so we've got this glass rod and we rub it with fur. So we rub it with fur, and we know that this rod, now we say it's charged because it can exert forces on things. You could use it to like lift up, like tiny little pieces of paper or something like that. So this object is charged. And he said if you touch this object to the metal, what happens is the rod becomes discharged, but that's it. The metal does not become charged. Whereas if you touch this rod to wood, to a wooden object, the wooden object becomes charged. So you can detect the charge on this wooden object as well. So that was kind of a curiosity, like why does a glass rod, let's go back to metal. Actually, let me just say one more thing here. If you do this, the rod and the wood will probably both be charged afterwards. So in one case, you touch the metal object and the glass rod loses its electrical properties. In this case, you touch the rod to a wooden object and they're both charged now. And so we need to explain what's going on here. And Charles Dufay came up with this idea. Let's go back to the metal. Kind of a clue is that the glass rod lost its charge. So what happened to that charge? And Charles Dufay reasoned that maybe the charge can flow through the metal and just go into the ground. And so that's why the glass rod loses its charge and the metal doesn't become charged because the charge just went through it. So that was his idea. It explains things. And why do we get different behavior with something like wood? Well, he said charges cannot flow through wood. And so, that's a good explanation. We have to test that though. And so what Dufay did next, let's say we have a metal object. And let's say we place that on a wooden base. So what Dufay was thinking here is if the charge can flow through metal but not through wood, it should leave this metal object charged because the charge can't get to the ground. That's where it was going before when the metal was in contact with the ground. And so according to his prediction, this metal object should become charged, and that is actually what happened. So that was one observation or discovery made in the early 1700s, that charges can flow through some objects. And again, I use metal and wood as examples, but there's actually a lot of different types of metal. And it seems like metal is it's a good conductor of electricity. So charges can flow through it fairly easily, where things like wood or plastic, a lot of other materials, charge does not flow through, and we call those insulators. So we have conductors and insulators. And now there's actually a third classification we learned later, something you've definitely heard of. It's called a semiconductor. The the most important example of that is silicon. It's a semiconductor, and they have very interesting electrical properties. But again, we're going to learn later how we can more precisely define like the ability of a charge to flow through a material. It's based on something called the resistivity. Like every material has a resistivity, and there's a huge gap between a conductor and an insulator. When we look at the numbers later on, it's not that conductors are just a little bit better at carrying charges than insulators. There's an enormous gap there, but there are some materials that fall in between. And so, semiconductors like silicon and germanium have very interesting properties that are essential to modern electronics. And so that's why they have Silicon Valley. The entire city is named after silicon because that's where they build computer chips and things like that. So, yeah. Okay, so that was one discovery, and they're a very important discovery. Charges can flow through materials. I think another more important discovery, we're going to look at another example. Here we've got this table, which I'll explain in a minute, but forget about that for now. What Dufay did is we have these two objects called pith balls, which are just very light objects. And so they're easy to move around because they have very little mass. And so let's say that we have them suspended next to each other. And let's use an example. And I kind of mark these elements like glass, or not elements, but materials. Glass and silk. You know what? Sorry, I'm going to rewrite this a little. Just move it over a little. Okay, so we have glass and silk. So we have a glass rod, and we rub it with silk. And let's say we take this rod and we touch each of these pith balls. Yeah, I just want to be clear which material is actually... So again, we touch each of these balls in turn. So you touch one, and then you touch the other. And what Dufay found is that they moved apart from each other. Okay. And then another example. We do the same experiment, basically. So we have two pith balls that are suspended by light strings, like a thin thread. They're very close to each other. And here we use sealing wax and fur. So we rub them together. And say we have this wax, and we touch each of these balls in turn. So you touch one and then the other, and you get the same effect. So they move apart from each other. Okay. Now, that by itself, okay, so it seems like we already discussed we can transfer charge. So what we know about charges already, they can transfer from one object to another just by touching them to each other. So we touch the glass rod to the ball, we transfer some charge, and it's a repulsive force, we can see. And we do it with wax that we charge by rubbing it with fur, and they move apart. We get the exact same behavior. But if you went one step further, I'm going to color these. So let's say this one we have, say, two, just color those red. Here we have two blue balls. Okay. And again, they're behaving exactly the same, but now let's do this. Let's take one of these strings and attach it here, and we'll take one of these and attach it here. So we have one red and one blue. And now what Dufay found is that these two balls are attracted to each other. So this was a very important discovery, because what Charles Dufay discovered is that there are two types of electrical charges. I haven't really talked about what a charge is yet. But there has to be two types. Because here, now I want to kind of jump towards a modern understanding of this. So, again, this was the early 1700s. And if we jump to the early 1900s, to the modern atomic theory of matter, basically for an atom, we have the main particle, the main parts to an atom. You have protons, neutrons, and electrons. Where protons are positively charged, we know we have two types of charge, and we call them positive and negative. It was Ben Franklin that gave it that naming convention, and so we're stuck with that now. And I said we're stuck with it. It's actually kind of unfortunate that it turned out this way. Not Ben Franklin's fault, but we'll learn why later it's unfortunate it turned out the way that it did. But anyways, we have atoms are basically made out of protons, neutrons, and electrons, where protons have positive charges and electrons have negative charges. Now, I mentioned that electrical forces are extremely strong. Out of the four forces, they're the second strongest. If you organize forces by strength, you have the strong nuclear force, then electromagnetic, then the weak nuclear force. It's more like, here, 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 and then gravity is like way down. And that might seem strange because gravity is so much more present in our lives, or it seems that way, it's so much more obvious. However, the reason why electrical forces do not have such obvious effects is because there's two types. There's positive and negative charges, and they occur in equal numbers most of the time. So like if you have an atom, let's just say we have an atom with 12 protons, it's also going to have 12 electrons. Now, it's possible it's going to have a slightly different number of electrons, because if we look at an atom, you have the nucleus, which contains protons and neutrons, and the electrons, for now, let's just picture them as like little balls of electric charge. Turns out that's not a very accurate picture. But, these electrons are outside of the nucleus, and so it's much easier to remove an electron from an atom than it is to remove a proton. If you want to take a proton out of an atom, you have to get it out of the nucleus, which is extremely hard to do. But electrons, much easier to move them. One way you can remove an electron from an object is by rubbing it with another object. And that's what we're talking about here. And so we have this kind of table here. It doesn't have numerical values, but it has an order of things. And I'm going to erase these. I was just looking at the kind of examples that they used, that Dufay used. So again, if we look at this table, this kind of tells you which... Okay, maybe I should have left that. I think we had glass and silk. Yeah, I'm going to leave this just for now. I'm going to kind of revisit Dufay's experiment, and then fur and sealing wax. So I'll erase that later. But anyways, just the ordering of things. Like here on the top, like glass tends to lose electrons if you rub it with another material. It depends on what you rub it with, though. So, let's just pick two things. Let's look at glass and silk. So if you rub glass and silk together, up on the higher you are on this table, the greater the tendency to lose electrons, and the lower one is going to gain electrons. So if you rub glass and silk, the glass is going to lose electrons, and the silk is going to gain electrons. So initially we had this glass rod, which had an equal number of protons and electrons, or an equal number of positive and negative charges. But now the glass loses electrons, and so it becomes positively charged. And so these red balls become positively charged, because just by touching it, some of that charge moves from one object to the other. So this red ball was positively charged. Now if we go to the other example, we have fur and sealing wax. So the fur is going to lose electrons, the sealing wax is going to gain electrons. And so the wax gains electrons, it becomes negatively charged. And then when you touch it to these pith balls, it transfers that negative charge. And so, going back to the two different types of charges, the reason why the behavior looked the same, even though there was a different type of charge, is that the general rule is charges exert forces on other charges, and like charges repel each other, opposite charges attract. So here are two positive charges. They're like charges. They're both positive, they're going to repel each other. Here they're both negative, they're going to repel each other. But here if you have one positive and one negative, then they attract each other. Okay, so a couple more things to say. Just for organization purposes, I want to see what's on this actual topic. Don't want to get ahead of things. Yeah, we're just going to talk about electrical charges. And that'll be it for this this lecture. So I mentioned, on an atomic level, protons have positive charges, electrons have negative charges. So there's a few important properties of charges. I can erase this now. Okay, so for electric charges, one very important property charges are quantized. So what does that mean that charge is quantized? Basically what it means is that there is a smallest amount of charge. And so charges in general, so electric charges, we use the letter Q. Just like, for mass we use M, for velocity we use V. Electric charge we use Q. You can actually use either uppercase or lowercase. Kind of like with mass, for ordinary masses I use a lowercase m. But if you're talking about like the sun or a planet, I often switch to an uppercase m. Kind of the same thing here. Now electrical charges are measured in units called coulombs. This was named after a scientist named Coulomb, who did some very important work in electricity. I think he was actually the first one to come up with a way to measure just how charged an object was. And his method was to shock himself and see how much it hurt. He actually, that was his method. Very devoted to science. But, yeah, so we have this unit of charge named after him. And so charge is quantized, which means we have something called an elementary charge. Which we use the letter E for. So an elementary charge is E, which is numerically equal to 1.6 times 10 to the minus 19th coulombs. Now I should say 1 coulomb would actually be an extremely large charge. So there's reasons a coulomb is used. We'll talk about more how that's defined later. But usually we don't deal with charges on the scale of coulombs. Usually what we use are microcoulombs. So remember the scientific prefix micro, that's 10 to the minus 6 or 1 millionth. So it would take 1 million microcoulombs to equal 1 coulomb. And again, this is a more reasonable unit of charge for most things. Unless you're on an atomic level, and then you'd measure things in terms of this elementary charge. Okay, so yeah, one very important property, charge is quantized, so that means that the smallest charge which we call an elementary charge, and it has this particular value. Now the charge on a proton, let's call that QP. The charge on a proton is plus E, and the charge on an electron is minus E. And so what this is telling us is that the charge on a proton and a charge on an electron have the exact same magnitude. They're different types of charge, but they're just as strong as each other. And that's our theoretical understanding of it. It's an assumption, but they've done experiments to test that. And they've shown to a very high degree of precision that the charge cannot be different by, much at all. So they can set limits. I think it's like 1 part in 10 to the 20th power or something. So like if the charge of a proton is E, the charge of an electron has to be like 1.000 of like, I don't remember the number, but it's some crazy number. So yeah, we're just to say they're exactly the same. There's other reasons for believing they're exactly the same. Okay. And so in general, now I should point out that this is called the elementary charge because that's a charge on a proton or an electron. Now, of course, atoms were first discovered, and they were seen as kind of like indivisible particles. So that was kind of the whole idea behind an atom. So you take an element like iron. You have an iron block, you cut it in half, well, you've got 2 pieces of iron. What if you cut it in half again? Now you've got, I guess if you cut each one in half, you have 4 pieces. But again, you keep cutting this iron in half, and you're going to keep getting more, it's still iron no matter how small you cut it. But, the idea of an atom is there's a limit to how far you can cut things. And an atom is like the smallest piece of a substance. And I believe that when they first came up with this atomic theory, they thought that's it. These atoms were kind of like the smallest particles you could have. But then they quickly learned that atoms themselves are made of things like protons, neutrons, and electrons. And then, of course, that raises the question, what's a proton made out of? And so they go deeper, they're made of quarks, things called quarks. And it turns out a quark has a charge smaller than this. It's 1/3 of this. There's different types of quarks, but you can have a charge equal to 1/3 of an elementary charge. So historically, this was seen to be the smallest. But we're going to kind of ignore that for 2 reasons. 1, it won't have any effect on what we do in this class. And 2, it doesn't actually change this basic idea that charge is quantized. It just means that the elementary charge is smaller than we thought, but it's still quantized. Okay, so again, for our purposes, this is the smallest charge, protons and electrons. Okay. So what that means, and again, there's all sorts of particles that, there's more particles that carry charges than just protons and electrons. But most matter is just made out of protons and electrons. So what we're going to do is we're going to say that all the matter that we ever deal with in this class, all the charges are just going to come from protons and electrons. And that's basically, not inaccurate. So in general, we can say that the charge on any particle or any object would be the number of protons times the charge of a proton, which is E, plus the number of electrons times the charge of an electron, which is minus E. So NP is the number of protons, NE is the number of electrons, and they have a common E, which we can factor out. So we can write it this way. So in general, the charge on any object would be the number of particles the number of protons minus the number of electrons times that elementary charge. Now, usually, typical case, is that the number of protons is equal to the number of electrons. And if that's the case, then the charge on the object is 0. You have the same number of protons and electrons, charge is 0. And again, that's normally what's going on here. Like, I've got these two markers. I mentioned that charged particles exert forces on each other, and it's one of the strongest forces in the universe. And again, every atom is made out of charged particles, and we saw how small atoms are. Like, each of these markers contains an enormous number of charged particles, and they're all exerting forces on each other. And, the electrical force between them, basically 0. Completely undetectable. And that's because, each marker has the same number of protons as electrons. Now, why is that the case? Well, you can look at it on an atomic level. Let's say that the number of protons, let's say you have a nucleus with, say, 7 protons and 6 electrons. Now, this is a very inaccurate picture because I'm drawing all the electrons like in this one circle, but just to illustrate the numbers. So we have 7 protons, 6 electrons. What this means is that this atom overall has a positive charge. And so what that's going to do is it's going to attract another electron. So if there happens to be an electron floating around, well, it's going to go and attach itself to this atom, and then this atom will be neutral again. Same number of protons as electrons. Again, you can look at large-scale objects. Like say we have an object here which has an equal number of protons and electrons. Let's say I take an electron from this object and remove it. So I grab an electron and pull it off. What's going to happen? Well, now there's more protons and electrons here. So this object is going to become positively charged, and it wants to attract this electron and pull it back. And so it's kind of difficult to upset this balance where you have an equal number of protons and electrons. Because as soon as you upset the balance, it wants to bring it back. So if you have an object positively charged, it wants to attract electrons and neutralize itself, become electrically neutral. And so typically things are not charged. Now, one way to charge things is by, rubbing them together. So here we have, we rub objects together, and what's happening is, like the electrons kind of orbit around the nucleus of an atom. They're much easier to remove. But it depends on what type of atom. And it depends, I guess not everything here is an atom. Well, these are actually not atoms. These are more complicated things, like wood. It's an organic material. It contains carbon, for sure. Other elements, but definitely it's primarily carbon, I would think, and maybe oxygen and hydrogen. Those are the main organic things. But, again, like how hard it is to remove the electron, that depends on what type of material we're dealing with. So if you rub them together, electrons can go from one object to another. So you can transfer charges, but again, it's difficult to keep an object charged because like here, if we have this positively charged object, it's going to attract negative charges. Kind of an example, on a very dry day, if you walk across carpet and then touch a metal object like a door handle, you get shocked. That's because you acquire you get unbalanced. Charges can flow between you and the ground, and so you become charged. And then when you touch a door handle, that's a metal object, you can get charges to, you get shocked. That's a flow of charge, which you can actually see and feel. And so the point is that you don't remain charged for long. Now, I'll say one more thing for this lesson. Charging things by friction, by rubbing them together, this is actually a very effective way of charging things. And so I'm going to post a video actually, something called a Van de Graaff Generator, where you can build up very significant charges on objects using something like a Van de Graaff Generator. But again, I think I'll just post a video so you can kind of see how they work. It'd be better than me explaining it. But the basic idea, you have this belt that you can charge it by friction, and then it moves up and transfer that charge to a metal, like a metal sphere. I'll post something. It'd be much better kind of explaining the detail of how that works. Kind of see it in action kind of thing. But yeah, again, you can really charge things up with that. So I think I'll leave that here. And next, I kind of broke up the notes into maybe a little too small. The next thing we're going to talk about is transfer of charge, which kind of talked about already a little bit. But we're going to talk about, one device in particular that can be used to measure charges. But that'll be a separate, very short video. So I'm going to stop this one here.